Section 2.6, Graphing Piecewise Functions. Before we get to graphing the functions, we need to understand the concept of continuity. So a function is continuous over an interval of its domain if its hand-drawn graph over that interval can be sketched without lifting the pencil from the paper. So for example, this function, it's continuous from -infinity to 2 because we can draw it without lifting the paper, but at 2 it's discontinuous because we'd have to lift the pencil and go over here, and it's continuous from here onward. So this is actually an example of a piecewise defined function as well, because this function has a different shape, different definition from -infinity to 2, and from 2 to infinity it has a different definition. So this is a piecewise function, and we'll learn how to graph these in a little bit. So here are a few examples. So this function, it continues across the board, right? Across the domain. So it's continuous over -infinity to infinity. This function is continuous from -infinity to 3, and discontinuous at 3, and is continuous from 3 to infinity. Discontinuous at x equals 3. So this is also continuous over -infinity to infinity because there's no gap at all. Same thing with this one. This one only defined from 0 to infinity, but it's continuous over its domain, or 0 to infinity. This function is continuous over -infinity to 0. This one is discontinuous at x equals 3 because there's a gap there. This function is discontinuous at x equals 1 because there's a gap there. Here are some graphs of common functions. The first function we look at is the identity function. So the identity function means that x and y values are always the same. F of x equals to x itself. So it's a straight line across right the middle diagonal of the coordinates. So x and y values are always the same. 1, 1, 2, 2, 3, 3, -1, -1, -2, -2. The squaring function, f of x equals x squared. So the values of y is always positive because any x value, negative or positive, when squared, it's going to be positive. It decreases from -infinity to 0 and increases from 0 to infinity. The cubic function, f of x equals x cubed. It increases from -infinity to infinity, and it's continuous across the whole domain. The absolute value function, f of x equals absolute value of x, has a V shape. It decreases from -infinity to 0 and increases from 0 to infinity. This is also continuous across the entire domain. Even though there's a bend here, it's still continuous because we don't have to lift up the pen. The square root function takes on this shape. It's only defined from 0 to infinity because we cannot have a square root of a negative number. So it's only, the domain is only from 0 to infinity. The range is also from 0 to infinity. So let's try graphing some piecewise defined functions. So this function f of x is defined as negative 2x plus 5 if x is less than or equal to 2. And it's defined as x plus 1 if x is greater than 2. Which means from negative infinity to 2, it's going to look something different than if x is greater than 2, it's going to look something different. So let's find that. So let's try the first part. So when x is less than or equal to 2, let's try an x. Let's find x and y. So 2 is included here, so we can use 2 here. 2. So when x is equal to 2, we plug into the first definition because that's for when x is less than or equal to 2. So f of 2 would be negative 2 times 2 plus 5. So that minus 4 plus 5, so that's 1. So we need 2 points to draw this because it's a line. So let's do x equal 1 because x1 is also less than 2. So f of 1, negative 2 times 1 plus 5. So that's negative 2 plus 5, which is 3. So we get 2 points now. So 2, 1, and 1, 3. So now we can draw the line. So the line does stop here because it stops at x equal to 2. Now let's find the other half of this graph. So for when x greater than 2, so let's use x equal to 3. So f of 3 would be, we plug into the bottom definition because x greater than 2. So f of 3 is 3 plus 1, which is 4. F of 4 would be 4 plus 1, which is 5. So 0.34, and f of 4 is 5. So this is the line. So this one we can extend down to 2, and then we use a open circle there at 2. This function f of x is defined as 2x if x is less than or equal to negative 1, and it's defined as x minus 1 if x is greater than negative 1. So at negative 1, that's where they look different. So let's do first x less than or equal to negative 1. So let's try f of negative 1. Since it's included negative 1, that means 2 times negative 1, so that's negative 2. So when x equal to negative 1, y is negative 2. Let's try negative 2. F of negative 2 is 2 times negative 2, which is negative 4. So negative 1, negative 2. When x equal to negative 2, it's negative 4. So that's the first part of the line. So let's do x greater than negative 1. So let's do x equal to 0. F of 0 is 0 minus 1, which is minus 1. Let's do f of 1. F of 1 is 1 minus 1, which is 0. So at 0, x is -1, and x equal 1, y 0. So that's the 2 points. And we can extend it down. In this case, when it's extended, they actually meet at the same point. So this function is actually continuous at -1, even though they are piecewise defined function as two different definitions there. This function is defined as x minus 1 if x is less than or equal to 3, and defined to be 2 if x is greater than 3. So let's do the first part, x less than or equal to 3. So let's do x equal 3. So f of 3 is 3 minus 1, which is 2. Let's do f of 2. 2 minus 1, which is 1. So from 3, 2, and 2, 1. Let's do the other part. So when x equals greater than 3, f of x is always 2. So this one, the y value is always 2 for x greater than 3. So that's just a horizontal line. So this function is defined as -3 if x is less than or equal to 1, and defined as -1 if x is greater than 1. So when x is less than or equal to 1, its value is -3. And if it's greater than 1, the value is -1. So -1. So 1 is not included here, that's why there's a open circle there. But both parts are horizontal line.